talk in greater detail today about the pre-G8K part of the workflow, and that is the required data processing to prepare the data for G8K. You're all familiar with how this works. Data comes off the sequencing machine in either an unaligned BAM or FASTQ format. The reads come off the machine, and namely you get essentially the name of your sample, the bases, and the qualities for each of those reads. You really don't know how to make sense of them. You don't know whether or not there are duplicates. And those quality scores, as we've heard, they tend to skew dependent on the machine and the preparation. So we know we need to recalibrate the quality. So when it comes to actually mapping your reads to the reference genome, essentially what comes off the machine is an enormous pile of short reads from your high throughput sequencing. And then there are different aligners that you can use depending on your data to essentially map it back to the reference genome. And we use BWA. There are a lot of aligners out there. We use BWA as we found it's sufficient for our purposes and has pretty good flexibility. So we use BWA for DNA, and then STAR version 2, the 2-pass approach for RNA-seq, which we'll talk more about. But the idea here is that once you map your reads back to the reference genome, everything has a home. Why is this a challenging problem? Well, as I said, there might be duplications in your reads, but also specifically finding the home for each read is a challenging process because of duplication in the native reference genome. We don't have all the samples in one place, so we need to reconstruct the picture, and often the picture is complicated to begin with. So when you're dealing with the enormous pile of short reads, in an ideal world, you know exactly where each one fit, and you'd be able to align them very easily. In the real world, what you have is specific reads that look like they could go in multiple places based on the number of repeat segments in your own DNA. Not to mention what happens when part of your read matches and part of your read doesn't match a potential clone on the reference genome. How do you make sense of indels or duplicated regions before knowing whether or not they mean something? So this is a challenging process. One thing that helps us up front is actually what we call paired end sequencing, which is a service provided by Illumina sequencers. And really what it helps is it reads the DNA. You get two reads in opposite directions. It reads the DNA forwards and backwards. And because you know the length of your read, you have extra confidence in the read having it both directions. So you have two ends of the same sequence that effectively help you know more confidently where to map a given read. And Geraldine showed this slide before, but really the ultimate output of your alignment is the sequence alignment map, the SAM file, or the binary alignment file. What's not pictured here is the header, which contains the metadata similar to what we saw in the VCF. It contains a lot of information about each record. And then the records are structured as you see here. The important things is that you've got the read name in blue, the flags linked to a dictionary, so each code represents a value in the SAM dictionary. You've got the position where your read has been mapped. A map quality confidence interval, that's the map Q score. We talked a little bit about CIGAR, and that is essentially a condensed alignment report that tells you about the structure of how it's been aligned. It has mate information there, which in pair end reads, you have a mate, that's a good thing. It means that it knows where it belongs. And then it's got the actual sequence, some quality scores, and then this metadata at the end, which is very important for us because you can store an unstructured amount of metadata about your read, preserving the information that came with the sequencer and maybe some prep. And being able to store that additional information really helps for troubleshooting. And that's why we prefer this file format, so we'll talk a little bit more about that. So in terms of how this actually happens, traditionally data comes off the sequencer in FASTQ format. And you use BWA, you run it through BWA to ultimately get at mapped bands. The challenge for us is that FASTQ as a file format doesn't have a home for all the additional metadata that you might want to keep in order to make sure that you understand the entire journey of each read. And so for us, rather than starting with FASTQs, we actually start with unmapped bands. And we have a conversion that's not shown here, but we take the unmapped band and convert it to FASTQ, run it through BWA to produce the mapped band, just like how it normally works. But then there's this other parallel process that takes the metadata from that unaligned band and, along with some other cleanup steps, merges it into the mapped band file so that you have the mapped band, the aligned information, and all the metadata that came along with it. So that's what we do for DNA. When it comes to RNA, Geraldine spoke a little bit about this, but something that's unique about RNA is essentially that it splits, right? As part of the traditional transcription process, mRNA actually, there's the removal of intron segments, these non-coding regions of your RNA. And so RNA-seq, as part of this process, aligning using STAR-V2. Basically, STAR-V2 works in a two-pass process. The first identifies these splicing junctions, meaning where the introns were removed, and then it uses the splicing junctions to guide the ultimate alignment. Now, that leads to really incredible sensitivity for the STAR version 2 aligner, but the challenge for us is that in the output file, specifically in those cigar strings, it presents us with this unique operator that GATK doesn't know what to do with, and that is these N values. You can see N10 over in the bottom right-hand corner. So, in order to make that data consumable for GATK, we use the split and trim function, which essentially takes those N operators and splits each read into two separate exons, and then subsequently trims the overhangs to make it consumable for the downstream step GATK. So two processes for alignments, one with DNA, one with RNA-seq, both with the ultimate goal of making the data consumable by GATK. But that's just the first step. That's just mapping to the reference. And the second piece that we'll talk about, and actually Khalid will talk about, is marking duplicates.